Okay, so good afternoon, everybody. So it's my pleasure to welcome you to this lecture series at the East African Institute for Fundamental Research. So we are giving this lecture series online. We have Professor Ana Sanpera visiting us from Spain. So she's actually here in Kigali at the Institute and is she's an expert in quantum information, and we thought it would be good for her to introduce us to quantum information and things related to quantum information, including the most famous. So it would be good to have this introduction to it. My experience has been that many parts in sub-Saharan Africa to quantum information, quantum computation. Yes, there's some groups in South Africa, some groups in Morocco, maybe a few other groups, but this is not something that's very common to us in sub-Saharan Africa. We want that to change. We want Africa to be part of the second quantum revolution. The first quantum revolution, like we know, was the introduction of quantum mechanics in like 1925. So this series will help us to learn a little bit more about what quantum computing is and what quantum science and information science and technology are. So this second quantum revolution is not limited to quantum computing. Yes, I know quantum computing is the hottest one and is the most famous one, but there are other aspects, as Professor Ana will tell us about. So you're welcome to this lecture series. There's a lecture series there's a lecture today as we're here. There'll be another one next week on the 15th, and a third one the week after on the 22nd. They will all be online. We'll record them so you can watch them and revise them later on. Okay, so I'm going to introduce Professor Ana, and once I introduce her, then she will start with her presentations. So Professor Ana Sanpera Trigueros, she has a PhD in physics from University Autónoma Barcelona in Spain. From 93 to 96, she was a research fellow at Oxford University in the UK. And then after that, until 98, she was an European research fellow at Université Paris-Saclay in France. Then from 1999 to 2005, she was an assistant professor at Leibniz University in Hanover, Germany. Since 2005, she has been an ICREA research professor at the group at Quantum Information and Quantum Phenomena at University Autónoma Barcelona in Spain. So during this year, she has been an invited scientist and visiting professor at different places, including the Kavli Institute of Theoretical Physics in Santa Barbara. There's also one KITP in Beijing, China. She has been invited to University of Maryland in the US. Of course, ICTP, International Center for Theoretical Physics. And her research interests are interdisciplinary. So she works in quantum information theory, entanglement, which you'll get to know more about, and also she does things in condensed matter, out of equilibrium open quantum systems. And of course, and very interestingly for us, she is also strongly involved in science education and science popularization. So I hope Ana will write a book soon for simple people to understand many things, especially in this second quantum revolution. Okay, so we welcome Professor Ana to give her talk and tell us about the two. Thank you, Ana.
Thank you very much for this nice introduction. It's a pleasure to be here, and it's something that I wanted to do it, as Professor Aquino was saying, that there is a big impact nowadays on quantum technologies, of course, quantum computation, but other technologies. I'm working very strongly on that in the European community, and I think that this is something that has to reach everybody, and it's very interesting that also some activities are taking here. So what I wanted to, let me see, first of all, if I will be able, if there is any question, I would prefer that you ask me, interrupt me. because I'm trying to do something interactive and it's a little bit difficult on the writing and not erasing. So, well, first of all, I want to explain very easily what it's these quantum technologies. And quantum technologies, they deal with the development of doing novel technologies using quantum physics. So the laws of the physics that describe the world at the microscopic scale. And of course, this is in this sense not new because we use quantum technologies since a long time ago. But this use of the quantum physics at the microscopic scale means the use and control of single atoms, single molecules, or few atoms. So it's really single particle effects. Okay, and this is something that until very recently has not been possible. So up for today, because these things is something that is going to change a lot. When we talk about quantum technologies, we talk about something that we call the 4 pillars of quantum technologies. Because these technologies, we know that they will have the potential to offer better methods to solve problems in communication, in computation, in simulations and sensing, but not only that, also in basic science. Okay, so we are interested in these 2 parts. Indeed, I'm a person who comes from basic sciences, my main research, and it has 3 lines that you see here, which are, and in particular, this is very important, education, and control and software. But education, it's a big thing because we will require a lot of people who is for these new technologies educated in quantum physics. And this is something that one has to make an effort on that. So these technologies, moreover, they are expected that they will have certain impact. So not in everything, but definitely in chemistry, in material science, to understand new materials, in biology, in medicine, in artificial intelligence, etc. So it's a technologies that we expect that it will have a clear impact in society. So it's not only basic science, but it also will have a clear impact in society in the same way that technologies had the first quantum technologies transistor had, so that we are all here listening one to each other thanks to that. So I organized these lectures in a very general way. So I wanted to talk a little bit, first of all, what is this quantum information science? Sorry, I see there is already an error here. And quantum technologies, what is all this thing about? What there is so much fuss, what people is too much talking about that, which part are true, which part are not true, which is the state in which we are nowadays in 2022. And then in lecture 2 and lecture 3, I would like to go more concretely to explain the importance of quantum communication and quantum metrology, and then quantum computing and quantum simulations. So the first thing that one can ask ourselves is why now? Why this thing has appeared now? And I think that it's fair to say that quantum technologies, or this second quantum revolution, it's now because there has been 2 very important developments. First, since the 90s, so 30 years ago, a theoretical development of what is quantum information sciences and what does it mean. But also, and definitely very important for technology, because if not, it will not be possible, experimental advances in manipulating and control quantum systems at the single particle level. So this very small picture that you have here, I show here, this is a quantum computer, I think from Google, which has, I don't know, 50 qubits when it's open. So it's a superconductor quantum computer at this moment, a huge quantum computer. Okay, but to give a better control of what do I mean by control, experimental control, this is a picture from the Oxford University, in which if you look very careful, in the center of this picture, approximately here, which I'm going to put it, there is here. Okay, there is a single ion, only one ion, and you can see it. You can see it with your naked eyes. So it means you can control everything around this ion. It's vacuum. There is not any other molecule. There is nothing. Okay, this is a vacuum chamber, and of course, in order to see that, just by the principle of uncertainty, you have to send a picture so that the atom it's excited and then it decays and it emits lights. Okay, and this is done in a very, very, very slow time so that one can see that. And it's just amazing that nowadays we are able to control atoms and ions in the at the single level. Okay, and like that, in an ion trap, you can have 10, 20 atoms with ions in this case, which are trapped and which you can address individually with a laser shining on them. So without this extreme control of the quantum technologies, of the capability of controlling, preparing, and manipulating quantum systems at the single particle level or at the few particle level, so it would have not been possible. So quantum technologies could not appear before because it was just impossible to have this kind of techniques. So if we have a very fast look on the review of quantum technologies, of course, I mean, quantum technologies start in 1900 when quantum theory is starting with Max Planck and the photoelectric effect. And then we would say that from 1900 to 1924, it was the establishment of the quantum theory until Heisenberg with a matricial formulation. So it took 20 years for the first thing related to quantum physics, which is the transistor, not important, super important, which has changed our society completely, for better or worse, I don't know, but completely has changed it. So then it took in between 47 and 60, there is a lot of developments. So the photovoltaic cells, GPS. In 1960, there is another grand revolution, which is the laser, which we use it for all the technology that we know. And then in the 70s appeared the computer, personal computers, telephones, etc. So this is what we call the first quantum revolution, and implications for technology we all know, so they are very huge. So in 92, and maybe this is something that I would like to mark, in 92 is a very special year in this sense, because there is Richard Feynman, which proposed that, well, he says that quantum systems are very difficult to simulate because they are quantum systems. So maybe one should try to simulate it not with a classical computer, but with something which is also quantum. So it's the first idea, a little bit of what is a quantum simulator. And his idea is very simple, which is the following. So same physics or same equations have to have the same physics. So if you have, and we know that this happens in many areas of physics, no? So if you have a set of equations, although you are describing something different, and the set of equations are similar, the physics that you are going to find it similar. But not only that, so in 1982, there is a paper which appears already in the 70s. There are some papers about this quantum, how to transmit information with quantum. But in 1982, already 40 years ago, there is a paper by Butters, who is the paper who shows that quantum information, so a quantum state cannot be cloned. A classical system can be cloned. We have the photocopies. I take a paper, we make a photocopy and we have it, but a quantum system cannot be cloned. And then it starts to be a series of developments. Already in 1984, there is the first protocol of quantum cryptography saying that quantum cryptography, which is the capability to communicate secretly so that nobody reads, this is a big aspiration for everybody, so can be done if it's quantum, and this is the protocol that we will discuss. It's called Bennett and Brasser 84. 5 years later, it's Ecker 91, which was not such aware of this protocol and proposes another protocol which uses entanglement, okay, for ensuring the security of quantum cryptography. And from 90 to 95, they start to appear some algorithms, quantum algorithms. And 1995, it's again a very important year, okay, super important year, because several things happen at the same time. First of all, there is the first really quantum algorithm, which is Shor algorithm, which shows why a quantum computer can be powerful compared to a classical computer. And in particular shows that a quantum computer can break any of the keys which are used for communication, for secret communication nowadays. And of course, when that happens, the world started to be a little bit aware that this was not only something which was just for fun of physicists and computer science working on something, but it can have a lot of consequences. In the same year, it was the first time that Bose-Einstein condensate, so control of matter to extreme points, was achieved. After 70 years, it was proposed in 1920, so it took 75 years to achieve that. And also, there is the first time that there is a computer, the idea of a quantum computer, how it should be, which is this Dirac-Soller idea of a quantum computer using ion traps, and how a control node, and we will talk about that, can be realized in order to make this computer. So from 95 until now, which is in this few years, the second quantum revolution goes very fast. And here the scale is only 14 years. So in 2006, there is the first quantum key distribution. This is to distribute a key and to have perfectly secure communication. It's established for the first time with a distance of 145 kilometers. And then in 2007 already there is the first, let's say, quotations commercial quantum computer is a D-Wave. It has 16 quantum bits. So imagine this is nothing. In 2010, IBM says that it's going to enter in quantum computation. In 2014, Google says that it's going to enter in quantum information, in quantum computation. 2016, just 6 years ago, Rigetti, just a student at the university, decided to found his own company. Okay, so this is the start of these startups. So not only the big companies like IBM, Google, and so on, but Rigetti Computer, which is now has 16 qubits, is just a single person from the university that decided to open a company. And at that time, IBM already has 5 qubit, which is open. Everybody can use it. It's a very bad computer, of course, with 5 qubits, as you can imagine. In 1917, China uses BB84, this protocol, using satellites. So it takes a distance of thousands of kilometers. In 2019, it's important because Google shows that there is a protocol. They are able to solve a problem which it doesn't have any relevance. So it's an invented problem. Okay, but if such invented problem which doesn't have any relevance for physics, for science, doesn't matter, was intended to do in a classical computer, it will take of the order of 10,000 years. So this is what it's called the quantum advantage, so that you can do things that in a classical computer you will not be able to do it, and we will express what it's that. And last year, quantum computer launched his quantum computer, which is now 120 qubits. And the idea is, and what people is saying, and this, well, it's, I don't know if it will be like that, so that when we are here in, no, it's not working that. For some reason, now I cannot write. So around 2030, we expect, or many people expect, that computers will start to work here. Okay, so this is the data that many people say will be true or not. Well, it's 8 years from now. I think, me personally, I think it will take a little bit longer, but maybe 15 years or something like that, we will have the first, we think the first computers. So I have to delete all these things.
Sorry, Anna, I thought
yes.
D-Wave now, they use more than 1,000 qubits, no?
Yes, but D-Wave, it's not really a quantum computer, it's a quantum annealing. Okay.
Okay.
And I will tell you the difference of these things. Okay, so it's not a universal quantum computer.
Okay. Okay. Thank you.
So well, I'm going to start very basic. Okay, so please excuse me if you find it very basic, but I think it's important to understand what it's the fount of that. Okay, so the foundations, why these things of quantum technologies and quantum information science it's about. So of course, if you talk about what is quantum information science, most of the people will tell you that this is using quantum physics, so the laws of quantum physics to transfer and manipulate information. This is true, but it's a little bit more extensive. And which are these laws of quantum physics? And the laws of quantum physics are many, but for me, there are 4, which are very important. Like these 4 truths that everybody should know. It's that every object is a wave and a particle. This is something that we know. So this is already since the de Broglie. And this is clearly demonstrated because we know that there is this thing which is the basics of quantum physics, the very, very, very basics, which is the double Young experiment, which you can do it with light, and then you see that you have interference fringes, but you can do it with electrons, and you know that you have interference fringes if you send the electrons one by one. You can do it with molecules, and you get interference fringes, and here anecdotically is written a virus and how big the objects can be. Well, of course, it cannot be like us because we are very massive, but a priori, any object can be will behave as a wave or as a particle. Okay, and as a consequence of that, this is the first thing that it's fundamental for all the quantum technologies. The first thing that we have is that indeed, okay, there is a superposition principle. And this superposition principle, what it tells us is that each object may interfere with itself. Okay? It's not that interference with another, interference with itself. And this is something that classically cannot happen. Okay? So this is the second thing, and quantum computing, it's very much based on the superposition principle. So what else? So the quintessence of the superposition principle is the Mach Zehnder interferometer. And this Mach Zehnder interferometer is exactly identical of the double Young experiment of the split, of the double split experiment of Young. Okay, so, and it's the one that shows us, and it's the basic also of quantum computing. So we will use it a lot. So, and we know that it works. It's very easy to make it work. So we know that what happens is that we have, let's see, right, yeah, yes. So we have a beam splitter, and a beam splitter when we put particles that I will call it zero because this is the standard thing. What this beam splitter makes is it creates a superposition of paths. Okay. So with a phase, although this is not so relevant. Okay. And then we have these mirrors, and the mirrors, what they make, so let me say even better, call this, because it's nicer, X, because it goes in this direction. Okay. So, and this will be, so let me put it in a nicer way. So that will be a superposition of something which goes in the X direction, and with a phase, it moves in the Y direction. And then you will have these mirrors, and these mirrors, the only thing that they do is that the X is changed by Y, okay, and the Y is changed by X. And then we have our second beam splitter here, okay, and I'm not going to do the maths, but after this second beam splitter, what we have is that the output of this second beam splitter is something like cosinus, and here we have a phase, okay, so we have to put this phase in this direction, and then we'll have something which is cosinus of plus or minus I sinus. It's very easy to move, so this will be our output. So whatever we have here after the second beam splitter. Okay, and this is very important because it tells us that if there is not phase shift, everything, so sorry, this will be X minus EY. Okay, and now we detect here. So if the phase is 0, everything will be in X. And of course, if the phase is pi, everything will be in I. But the important thing is that this is interference. It's interference of a photon with itself, if we want, of an atom with itself, and this is the basic that we will use for everything. So let me erase all these things are here, because if not, they are. So this is the same. So there is another fact that we all know from quantum mechanics. For me, these are the 4 truths of quantum mechanics, is that measuring may change the state of the measured object. Okay, and this is something that we will also use. And finally, there is another thing which is new, which is that there is entanglement. So they are correlations, which are quantum correlations that they don't have an analog to classical correlations. And basically what it tells us is that if we have 2 systems that I will call, I don't know, A and B, so this is my system A, and this is my system B. So the description of AB, definitely, if there are correlations, it's not the description of the system E plus the description of the system B. And this is what quantum correlations, classical correlations also mean that, but classical correlations, we can always move it, but quantum correlations means that whatever I describe perfectly the system A and perfectly the system B, this is not a description of the whole system. And this is also the second big thing that we will use for quantum technologies. So quantum technologies will be very much based in superposition and entanglement. So if we say that, so what is quantum technology? So what is quantum information? So quantum information is to use quantum mechanics to prepare, to transfer, and to process information exploiting superposition principle and quantum correlations. This is the minimal definition of what is this quantum information. So, and now we need very few things at the very basic level that I would like to use because it allows to understand everything. First of all, something that we know that quantum mechanics is a linear theory. So it's given by linear algebra, so by matrices. Okay, and of course there are things that we know already that matrices, they do not commute, so that makes the physics quite different from the classical thing. But the important thing here, and this is, it's very basic because quantum information is just using things that in some way they were overlooked, but now we can really use these things, okay, to do something in some way. So normally what we do is that we describe our systems, okay, so we describe systems, but this we all know, and I will say which kind of systems, by a Hilbert space, okay, a Hilbert space, and this is how we are used to use the quantum theory. And we always use, because it's much easier, this Dirac notation, which I already used it when I was explaining the interferometer, which is a state will be phi. And in particular, we use two-dimensional systems, and I will say why two-dimensional systems. Of course, because this are going to be qubits. And these two-dimensional systems will have a basis, which is called the computational basis, which is a 0 and a 1, as simple as that. And any other state, of course, can be written as a superposition of 0 plus 1, where, as we know, alpha and beta are complex numbers, and these have to sum the identity. And operators, which are the transformations that we can do over our states, are linear. So 8 times phi plus, and this is very important because if not, the world will be very different, as we know. But this is nothing else than A over phi of psi plus B of operator A acting on phi. Okay, this linearity, okay, is the responsible that quantum systems cannot be cloned. Okay, so if there is not any unitary operation that will fulfill something like that, and we can understand, and we understand it in a very simple way. Okay, so we say that my way to write these operators, these operators are just maps that they go from a Hilbert space to a Hilbert space that it can be the same or not. So given a state, so it's a map, so it's a matrix, will be applying this matrix over my vector and will give me another vector. Okay, so far so good. This is what we have always heard that. So let me delete all these things so that I can go to the next, because I wanted to do it slowly and that we can see it. Okay, so we have these three things which are easy, which is in one side we have states, and by states we'll say, well, if our state is isolate, will be given by a vector of the Hilbert space, as we know. So this is isolated states, And we know that if the state is not isolated, it will be described by an operator, which is a bounded operator on the Hilbert space, which normally we call it a density matrix. And what does it mean that here? Well, it means that if we have a system, A, which is interacting with another system, which can be the universe, B, okay? And this system, and this is the whole universe, this system, it's closed and it's described by a vector AB. But if now, because we cannot observe the whole universe, we want to observe only this part of here, okay? This part of here will be described by a density matrix because we have to trace out the universe, okay? And tracing out the universe means to trace B out of my state. And it's as simple as that. Okay, so we have for isolated systems, or when the system is not isolated and we have to work with that, we will describe that by a density matrix. What else? We have transformations. By transformations for isolated systems, okay, so quantum mechanics tell us that for isolated systems, this is a Schrödinger equation, okay, so transformations are unitary, okay, so are transformations such that this is the identity. So they have to be unitary. And this thing, a unitary transformation, is what we will call it a gate, a quantum gate. It will be like that. And then we have measurements, well, that we know that quantum mechanics tell us that we have a measurement. So if we have a system and we have a set of operators, okay, which are positive, that I will obtain, okay, this is the probability that I obtain the output M when I measure on phi. And all these things of here, I'm going to represent it like that when I'm going to do in this is faster now. Okay, so all these things which are quantum mechanics, right? The first lessons, but they are not trivial. I mean, it's easy mathematically, but the things have to be understood, and we know that always understand it's a little bit more difficult. So we can put it like that. Let me write what I wrote before, so it will be something like that. Okay, so I will have a system. I will have a unitary transformation, and then I will have a measurement. So this is the most basic quantum circuit you can imagine, and this means my physical system, so psi, my transformation, and whatever it goes out, psi. Okay. But now we have to say why we use qubits and what they are qubits. So everything that we do in quantum, almost everything, not everything, that we do in quantum computing and quantum communication, it's with qubits, okay? So a qubit, as you can imagine, is just system, which it has two levels, okay, which I'm going to call it 0 and 1. So an atom with two levels which are well differentiated, the ground state and the first excited state, or spin of an electron, which can be up or down along one direction, or any other thing that you can invent, which has two levels, which are well separated, and that they can be addressed independently. Okay, this is fundamental. So, and now we will write that in my basis, this will be this vector. This is the computational basis. Okay, so that means I have my, for instance, if it's a two-level atom, okay, and when I'm talking about two-level atom, I'm talking about the electron of the external. For instance, it can be the external electron that I have in an atom that it has these alkalines, so that they have one electron in the s orbital, okay? Or it can be a Rydberg atom, or can be something like that. Okay? So this is 0. And if I want to write 1, so that I have my atom which is excited, or my spin which is in the, this is like that. Okay, so this can be spin up along the z direction, for instance, and spin down along the z direction. It can be any of these things. And now one can ask ourselves, why qubits? Okay, so what we are going to have, it's normally n qubits. So the name qubit obviously is because it's a quantum bit, because it only has 2 states. But normally what we are going to use is n qubits. So imagine that I have 2 qubits. If I have 2 qubits, now I will put it like that, 1 and 2. And mathematical, the way to write that it's with tensor, product of tensor, and then I will have a state which maybe it will be, I don't know, that my first qubit is, my first 2-level atom is in the ground state, or my first spin is pointing up in the z direction, and the second it's pointing up, for instance. And this, normally we write it like that. We subtract that and we put 0, 1. Okay. And of course, if we have n qubits, yes, sorry.
I have a question. So why do we typically use 2-level systems? Because
Okay, this is
like a 3-level system or 4-level system.
This is what I wanted to show now. Imagine that I have n qubits. Okay, so let me delete here, and now let me put it here. Okay, so normally we will have n qubits. And why? This is a very good question. Why do we have that? So our idea will be that we have, okay, I'm not going to write the tensorial product. So I have n qubits. Okay. So how many elements I have in this basis? Well, of course, in this basis, I have 2 to the n, which is very huge. Okay, because I can have, so for instance, the 0, 0, 0, 1, 1, okay, which will be this one of here. The first in the ground state, the second in the ground state, the third in the ground state, the 4 in the excited state, pam, 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 the last one in the excited state. So I have 2 to the n elements, okay? So now if I want to prepare any of these 2 states, and I have n, so 2 to the n states, and n qubits. Okay, so you could say, as you were asking, why I don't take a system like, for instance, this one, an harmonic oscillator. Okay. And I have also that it has 2 to the n states. And I have everything in a quantum system. Why I don't do that? Well, the reason is the following. These 2 systems, they are not equivalent. Because if I have to have, so I say that I have to have 2-level systems that I can address individually. So how many operations do I have to have in my system, in this one, in the n qubit, to reach this configuration, or to reach this configuration? It doesn't matter, 1, 1, 1, 1. How many operations I have to do? N. Okay, I have to address the first qubit, the second qubit, the third qubit, the fourth qubit, so n times. Now, how many operations do I have to have in order to prepare all these states? In particular, if I want to prepare this 1, 1, 1, 1, 2 to the n operations. And here I have n operations. Well, as you see, n and 2 to the n, it's very different. So if I have a single system with many states, and I want to have control of all the elements of the basis, that mean on all 2 the states, in a single system, I need an exponential number of operations. While in a system of n qubits, I need a linear number of operations. And this is the big difference. So whatever we do here, we cannot do it here. It's just out of question. So that is a very good question. Okay, so unless we have something very particular, of course, if we want to simulate a spin 1 particle, we will simulate it with a spin with 3-level atoms, okay, because that, or 3-level or a Q-treat, that it's clear. But a priori, we will see that everything we can do it just with 2-level systems. So the thing which is important is that n qubits, okay, have 2 to the n basis element. and requires n operations to manipulate it. And one system with 2 to the n elements or basis elements or levels, let's put it like that, it's not levels. Requires 2 to the n operations. So immediately that tells us that this, we can forget it. It will never be used. What else? So this, what concerns quantum systems and why everything we are going to do it in quantum bits, okay, with 2-level operations. Now we have to do, this is the same operations. So now let's just draw a very simple example. So we will have 1 qubit operations. What will be that? Well, that will be anything which I will represent it like that. It will be my 2-level system, which it will be this thing of here. I will put a unitary. That will be my gate. And going out of here, I will have my 2-level system in whatever state it is. Okay. So this is, I will write it always like that. So not to draw so much. So this is a quantum circuit, a trivial one, but this is a quantum circuit. Okay. So, and now when we talk about quantum circuits, we will do the following. We will take into account. Okay, so what we are going to do? Well, when we draw a quantum circuit, then you will understand everything very simple. It's I will have, I don't know, maybe more than 1 qubit. I will have something like that. Here I will have a gate. Then I will have a gate that takes 2. Then maybe I will have, I don't know, let's say that it takes 3. Then I will have here another gate here, and then nothing, and then maybe, okay. And then at the end, I will measure. Okay, and these are unitaries. Unitaries. So when we see something like that, we understand it immediately. This is a quantum circuit that has an input. This is my input, 3 qubits. Okay, and now I have to say, and it's a circuit of which size? Well, the size is the number of gates. Number of gates is my size. It's the size. Okay, so here it has 1, 2, 3, 4, 5, 6. But this is not very important. What is important is because this is time. Yes, all right. Wow. Okay, so this is time. This is unitary evolution. So what is important is the depth of the circuit. And the depth of the circuit, it's nothing else than taking that and saying, at each time, how many gates do I have? Here I have 1, 2, 3, and now I have 3. So the depth of this circuit, it's 4. And this is the important thing, okay, that we will see. But this is just details, which are not so relevant. So what I wanted to say, so this is how quantum computation will go, okay? And of all the gates, and we will be talking next day or the day that we do it, I just wanted to go to the 2 things. So I say that for doing any kind of computation, we need 2 things: superpositions and we need entanglement. Okay, so superpositions can be superpositions of a single qubit. So we have to see how it's the superpositions, and this is something as it's like that. Okay, this is circuit in which I have a gate which is called Hadamard, and it's very important, and that's it. So this Hadamard gate, okay, what it makes is the following: if my input qubit is in 0, it makes a superposition, and if my input qubit here it was in 1, so in the excited, okay, it makes a superposition with like that. But this gate is unitary because now we have to write. When we do that, we have to write the gate. And how is this gate? Well, this gate is 1 square root of 2. This is 1 square root of 2. 1, 1, 1 minus 1. And it's trivial to check that A DACA is the identity. You have to take into account that this is also very important because classical computation, it's not reversible, okay, when you do it universal. So, but quantum computation, because it's unitary, is reversible. So this is why it has to be unitary, it's because Schrödinger equation is unitary, it's a Hamiltonian. Okay, it's the exponential of a Hamiltonian, this is a unitary, which means that that doesn't require energy, okay? Energy is lost when you delete information, but here we don't delete information. This is another thing which is important to take into account. So this gate, it's very important. It's very important. So it's the basis of quantum, it's the basis of quantum information, and I will put it like that. Hadamard. Well, and now we have another gate, which I will put it like that. Whoops. Okay, which is a phase gateway, which is a phase gate, which is a gate which is of this form. It's also a unitary, 0, 0, a to the I5. Okay, so what this gate makes? Well, it makes the following. If my input here is a 0, it makes nothing. And if my input is a 1, it gives a phase, a to the I5, 1. Okay, so these are the only two gates which are indeed important. This Hadamard gate and this which is called the phase gate. And why they are important? Well, because this is the superposition. Okay, so if now we look at that, let me write you the Mach Zehnder interferometer. Okay, and the Mach Zehnder interferometer is this thing of here. And this is what it's in the Shor algorithm and in all quantum algorithms, in many of the quantum algorithms, okay? Superpositions. So now it's very easy to say that if I have this thing, now here I put this phase, it's written like that, it's a unitary operation, and this is H, okay? And now if my input, it's 0, after going through all these things, Hadamard, phase, Hadamard, the output will be the following. It will be cosinus of phi over 2, 0 minus I. This is my output. It's trivial to write because we can multiply the three equations, but only seeing, okay? So why this guy makes? It makes superpositions. What this gate makes, it puts a phase in one of the paths of the superposition. And what this second Hadamard makes, like the interferometer, is the second beam splitter. It unifies the two paths in order to have interference. Okay, so this is exactly the same as a beam splitter, a mirror, a phase, a beam splitter, a mirror, a phase, and here we will have interference depending on the phase. So this is the most important quantum circuit, I can say. And now we need the second one, which is to create also entanglement. Okay, so let me write that and I will finish here. Okay, so we need to create entanglement because entanglement will be very important, fundamental. So why quantum technologies are important? This is what I wanted to say. Not because they do something magic, it's because they use resources that classical physics doesn't have. And these resources are quantum interference and entanglement. That's it. Okay, there is no more. Okay, so, but these are very powerful resources. So if we want to go to, I can do it here. So this superposition entanglement. Okay, so entanglement is something that it depends on composite systems. So this is fundamental. So it's correlations between, these are correlations. Oops. Can be that I don't have. Okay. Correlations between composite systems. Okay, And to see these correlations, well, we can see how we can do it. So it's very simple. So let's first understand what does it mean, this entanglement. Okay, and let's start by a very simple case. So what happens is that we have our system, which is entangled with another system. Okay, and what I'm telling, so this is my qubit system 1, which is entangled with my qubit system 2. And I want to look at this single system. So this has Hilbert 1, a Hilbert space of 2, okay? And so the dimension of this guy will be a Hilbert space, which is H1 times H2. And if it's two-level systems, the dimension will be 4. Okay, so now before I was writing that, and I was cheating a little bit, I say, okay, how is a guy? So let me call this guy is A and this guy is B. So how is phi of I B? Okay, so well, of course I can write that something, it's like, for instance, something on A times something on B, a state in A and a state in B. So for instance, imagine that I say that this is 0, 0. Okay, so that corresponds to the first guy is in 0 and the second guy is in 0. But this doesn't have any entanglement because I can describe the system A and the system B separately. Well, imagine that I have another state, which is like that, another one, AB, which is the first guy, it's in a superposition of 0 plus 1 in A, and the second is in B, in 0. Okay, so this will be something like that, 0, 0 plus 0, 1. This is a product state because it's something in the state A and something on the state B. But imagine that I write this state, which is absolutely possible, 0, 0 plus 1, 1. Okay, this can never be written. You can try, look all possible states, like a state which lives in the space A, like a state which lives in the space B. This guy, it's what it's called entangled. I cannot prepare it, preparing A and preparing B separately. What it has happened is A and B has interacted, and therefore they are entangled. Okay, so this is a very powerful resource that we are going to use very often, and which is the second ingredient of quantum technologies. So I think I will finish here so that it's already long and you must be tired. But I wanted to tell you that, or to remember from here, that quantum technologies use as a resource quantum superposition and entanglement. And with that, we will see in the next lectures, you can do things that are not possible to do with classical mechanics. It doesn't solve all the problems, not at all, but it can solve some problems that they are not possible in classical mechanics. If there is some question or something, I will be happy to answer, and if not.
Okay. Thank you very much, Anna.
Okay, you are welcome. I hope it's clear, and I can show you next week's very nice things of quantum communication, like it's this cloning, teleportation, quantum cryptography, and why quantum computers are doing what they do, which is something that I will show in the next lectures. Thank you very much.
Thank you very much, Anna. Do we have questions for Anna? Actually, Anna, I have 2 questions, but I'll let other people ask. Do you have questions for Anna? Let me ask my second question first, so that, because I don't want you to erase this page. So in the last line, this yes, we cannot do because we retain the basis 0 and 1, right? But if we rotate, use a different basis, would we be able to write it?
No, no, this is not basis dependent. This is a very good question. This is a very good question. But if 2 particles, they are entangled in this basis, when I do a basis rotation, okay? Well, I mean, it depends what you want to say. So if you want to rotate this all together, a unitary that applies to that, definitely this will be entangled. if you are telling me that you are going to apply a unitary in one system and a unitary in another system, so you rotate differently, you can break the entanglement. Okay, but a global unitary can never break it. Okay, so it's not basis dependent.
Okay, thank you. Yeah. Are there other questions? Okay, and while I'm waiting,
I think it.
Okay, someone has a question.
Yes, you can. Yes, you can have much more than two particles entangled. Yes, but I will tell you that the only thing that it cannot happen is if it's Alice, which is a party, it's maximally entangled with B, then it cannot be entangled with anything else. So this is what we call that entanglement. It's monogamous. Okay, but if they are not maximally entangled, so this is a guy which is maximally entangled, this one that I was drawing. So if I have these two guys which are in a singlet, okay, so this is normally put like that. Alice and Bob, they cannot be entangled with anything else. But if they are not in a singlet, so they have less entanglement, then they can be multipartite entanglement. I can entangle 3, 10, okay. Wait, it was a question and I lost it.
Yeah, so Sonia has a question. Hi, Sonia. She says, thank you for the nice lecture. Is Berry phase important for quantum information?
Yes, for some things it's important, yeah, but not for the things that I'm explaining at this moment. Okay, so for some things it's important, yeah.
Okay. Thank you. So Anna, I want to ask you a question about the collapse of the wave function.
This is very difficult for me.
Yeah. Okay, this is something that has intrigued me and I think many other people. So when we think about the collapse, why can't we just think that when you measure, you are changing the Hamiltonian instead of just think that it collapsed into a state, right? Because the Hamiltonian is not the same Hamiltonian as before. Your measurement introduced superposition.
Definitely, yes.
Okay.
Yes,
so
yes,
then,
I completely agree with you, but this is a very complex thing. Yes, I completely agree. So you have an apparatus and the apparatus interact with the system and therefore you have changed the Hamiltonian and therefore then you take out, okay, all the information. But the problem, I would say that the way to talk about the collapse is an easy way to talk. The problem is normally your apparatus, well, you know, this is a huge field of research and it will always be. Normally the apparatus has many degrees of freedom and to track all these degrees of freedom is very complicated and very complex. So a very easy way to say is the wave function has collapsed, but I completely agree that this is a horrible explanation. It's a horrible explanation. I completely agree with you.
Yeah, that's good. Yeah, thank you. Okay. So we can take one more question if there's any other question.
So thank you very much for attending.
Okay. Okay. So I think we can thank Anna at this point and then we'll meet again at the same time. Yeah. Thank you very much, Anna.
Okay.
Yeah.
Thank you. Thank you very much to all of you for your attention.
Anna, we should make the slides available to us.
Well, the slides, I will pass it. I mean, the problem is that if I wanted to do it interacting, I cannot keep the slides written. So this is why I have to delete. It's a little bit complex, but I will pass it to you. No problem.
Okay. Yes. And then the recording will make it available also.
Okay. Thank you very much.
Thank you, Prof. Thank you.
Okay. Bye. Bye.
Yep.